Hi, I'm Justin. I'm going to talk about almost Chor Goldreich sources and adversarial random walks. This is joint work with Dean Doron, Donna Moshkovitz, and David Zuckerman. So the driving theme of this talk is randomness in computation. We know that randomness has proven to be very useful in computer science. It's useful in randomized algorithms, and it's necessary in cryptography. And usually in these applications, you assume to get your guarantees and for your analysis that you have uniform uncorrelated bits as your randomness to feed into these applications. So if you use n bits of randomness in your application, you would want to assume usually that these n bits are all uniform and independent from one another. And so a natural question is, what can be done if you don't have such amazing randomness? What can be done with the randomness you might have on hand, which might be weak or low quality randomness? And so why is this a natural question? Well, for one, the natural sources of randomness that you might find in nature or engineer might be defective. They might not actually be uniform random bits. There are many, proposals for how to get true randomness, but these might not be a completely uniform randomness. And so also there's the fact that many times if you condition on partial information about your source, then you'll get a weaker source of randomness after the conditioning. And this might come up in applications such as in cryptography, and it might come up in the analysis of whatever application you are using your randomness for. And so the ideal goal is you would like to purify these weak sources into nearly uniform sources so that you can feed them into your applications. And short of that, if it turns out that it's not possible to purify your weak sources like this, then you'd want to hope that you can purify your weak sources into a source that is good enough for applications, such as randomized algorithms. And so the idea in this work is we want to try to do this purification procedure via random walks. So as a background, there are traditional and many classic results that say that if you take a random walk on a high quality graph, then this random walk will mix well if you assume that each step of the random walk is uniform and independent. So what might happen is you might have a graph and you might have an arbitrary start vertex, and you might take first a uniform random neighbor to go to, and then after that use additional randomness to take another uniform random neighbor of the current vertex, and so on and so forth. And this idea is not very useful for purification, because if you are assuming that you already have uniform and independent steps to use, randomness to use for every step of the random walk, then you already have the best possible randomness you could hope for. And so the random walk is not really purifying anything to begin with. And so a natural question that we need to ask in order to make this purification work is we need to ask, can a random walk from a weak source on a sufficiently high quality graph also mix well? And so the main result of this work is that we can show this is true. So the main result says that we can purify certain types of weak sources. Namely, what we say is that we can purify what's known as a Chor Goldreich source, or CG source henceforth, which we define later. This is a very natural definition of a weak source. What we can say is that we can use this CG source to run a random walk on a high quality expander graph. And what we can say at the end is that the resulting vertex distribution is good enough to simulate randomized algorithms. And so this is the first known result that shows that random walks from weak sources can mix well. And this is a little bit surprising because actually in general, for general weak sources, we know that there are natural counterexamples that say that it's not possible for random walks to mix well. We'll talk about that shortly. And this is also the first known result to show that there is some sort of deterministic purification procedure for CG sources. This is also surprising because it was known also that for the much stronger notion of purification known as extraction, that there is no deterministic extraction procedure for CG sources. So I'll first go through some quick background. So first, I'll give some background on what is the measure of the quality of a source. Usually the measure we think of is min entropy. So if you have a random variable x on n bits, then the min entropy of x, denoted h sub infinity of x, is just the negative log of the most likely outcome of the distribution of x. And usually we're going to denote the min entropy of a random variable x as k, and we're going to denote the entropy rate of a source, delta, as k over n, the entropy divided by the total length of the random variable in bits. And also a very useful fact about min entropy is that if you have a random variable x distributed on n bits with min entropy k, then usually without loss of generality, you can just assume that X is actually a uniform distribution on some subset of size big K equal to 2 to the little k. And so now I'll give some background on the tools used to purify these weak sources, which is randomness extractors. So the natural question here is there a function X, which stands for extractors, which takes as input your random variable X on n bits and outputs m bits, such that for any random variable X with sufficiently high min entropy, the output of X is statistically close to uniform. And so the answer is no. It's well known that such a function is impossible. And so we're going to have to circumvent this impossibility result. And we'll do that in two ways, specifically in this work. First, we're going to assume that X has additional structure. This is this additional CG notion of weak source. And second, we're not going to aim to output something that's statistically close to uniform. We're just going to aim to output something that's good enough for applications. So now I'll talk about what is this additional structure we'll assume on X. What is this notion of a Chor Goldreich source? So I'll give you the formal definition first. So a delta CG source is a random variable X that is actually a sequence of T random variables for some growing number T, where each random variable Xi is distributed on D bits for D, which we usually think of as a constant. And the property that we want is that for every I in T and every possible outcome of the previous I minus 1 variables, it's still the case that the min entropy of the next random variable, even conditioned on the outcome of the previous random variables, is at least delta D, or has rate at least delta, entropy rate at least delta. And so the way you should visualize this property is as follows. So you're thinking of the CG source as a randomness stream coming at you one at a time, from X1 first, then X2, and so on. And what you should visualize is, let's say you draw out all the random variables X1 through Xt horizontally like this. And for each one, you draw the entire probability space of what the possible outcomes are. Since we said that each one is distributed on D bits, this is just the space of all D bit strings, which is of size big D equals to 2 to the little d. And the property of the CG source is saying that no matter what the outcome of the previous random variables, so let's say here you saw that the outcome of the first 4 random variables were these blacked out boxes, then the possible number of outcomes, essentially, of the next random variable has size at least big D to the delta. And so specifically, one of the main points of a CG source is that this subset of possible outcomes for the next random variable can be arbitrary. Namely, if you have a different set of outcomes for the first 4 random variables, so say maybe not these blacked out boxes, but some other set of outcomes, say 0, 0, all zeros or something, then the set of possible outcomes for the next random variable X5 might be a different subset of possible outcomes of size D to the delta. And so, like we suggested before, it's known that you cannot deterministically extract from CG sources. This was shown by Chor and Goldreich. So you cannot hope to have a deterministic function which just takes as input these random variables and outputs something statistically close to uniform. And so what we'll do instead is we'll give what's called a deterministic condenser for CG sources. So to set that up, I'll first talk about something called entropy gap. So first, let's say you have some random variable z distributed on m bits. We say that the entropy gap of this random variable is delta, which is equal to m, the length of the random variable, minus the min entropy. So you can think of this as sort of the number of bits of entropy that is deficient or is missing from z compared to the uniform distribution on m bits. And so the main observation is that z's with constant entropy gap are still useful in the sense that they're still close enough to uniform in some sense to be used for your applications such as randomized algorithms. And the way to see this, the intuition is very simple. So usually in a randomized algorithm, what happens is you sample if you use m bits of randomness, you sample a uniform random string from the space of all 0, 1 strings of length m. And there is a very small subset of bad strings for which if you end up sampling them, then your application, your randomized algorithm will fail. And so that means that if you're sampling uniformly, then with very high probability, you won't sample a bad string. And so you will still succeed in your application. And the observation is just that the same analysis or argument will hold not even if you don't sample from the entire space of n-bit strings, if you only sample from a large enough subset of n-bit strings, and a z with constant entropy gap is essentially just a sampling from a very large subset of 0, 1 strings. And so the main theorem of our work is we can say that for any entropy rate delta and any error parameter epsilon, there is some explicit function condenser which takes as input your CG source of any entropy rate delta and outputs a string of length roughly 0.99 delta dt. So here delta dt is roughly the amount of entropy that you deserve from the delta CG source. And we're saying you can output something roughly as long as the amount of entropy you deserve. And what we can say is that the output of this deterministic condenser, this deterministic function, is epsilon close to a source with a constant entropy gap. So what we're saying is we can essentially extract out or condense out almost as much entropy as we deserve from the delta CG source, and we can get it into a output random variable that is still useful enough for applications. And so this is actually quite a surprising result in some sense. So in order to see why this might be surprising, you can think concretely of an example of a CG source with d equal to 1,000. So each block of d bits is of length 1,000. And in each block, there's only 0.01 bits of total entropy. So what this means is that each block of this CG source looks almost useless in terms of what we deserve or what we could hope to use for randomized algorithms. Namely, each block of 1,000 bits looks almost entirely deterministic. Delta, if the total amount of entropy in each block is much less than 1, it means that these distributions each block's distribution could be entirely concentrated on a single outcome almost. And so a priori, this source looks almost completely useless in terms of how you could use it in an application. But it turns out that it's surprisingly that you do deserve to be able to use these types of sources in your applications. And there is a deterministic function that can convert any of these sources into a source that is good enough for randomized algorithms or other applications. And so now I'll talk about the techniques we use to construct this explicit function cond. And so like we suggested, the main ingredient to construct this condenser is via random walks. We just want this function cond to be the function that takes as input its random source and uses that random source to run a random walk on a graph. And so the question what we'll show is that we'll show that a random walk on a graph, a good enough graph, using a delta CG source for any entropy rate delta, mixes well, meaning that it results in a vertex distribution with constant entropy gap. And so, like we said, this is a little bit surprising because we know that for general sources with entropy rate less than or equal to 1/2, random walks don't mix. We know that they're actual counterexamples. For example, you can think of the example where the source is as follows. You alternate between a uniform random step going to a uniform random neighbor and a completely adversarial and completely deterministic step given that previous step that tells you to go directly back to the vertex you came from. And so what this random walk will do basically on any graph is it'll just go back and forth between the start vertex and another vertex, and you'll never get anywhere in the graph. You won't be mixing at all. And so what we're showing here is that if we have this additional structure from this CG source definition, then we get a result that shows that random walks with entropy rate less than 1/2 can in fact mix. And so just so that we're all on the same page, what we should picture for the random walk is in the standard case, when you take a random walk using true random or uniform randomness, you can be at a certain vertex as your current vertex, and in your next step, you'll pick randomly among all your big D equal to 2 to the little d neighbors to go to for your next step. And in the case of a random walk on from a CG source, you won't be picking a uniform neighbor among all edges. You'll only be picking a uniform neighbor among a small subset of edges for your next step. And you should note that in this scenario for CG sources, this random walk can be adversarial in the sense that wherever you're at, whatever current vertex you're at, the next distribution, the next subset of possible choices you can make can be completely arbitrary, meaning that an adversary could pick this subset of d to the delta possible choices for the next step to be as bad as possible in some sense, to prevent mixing as much as possible for your next step. And we'll talk about that in just a second. And so I need to tell you now about what types of graphs will facilitate mixing using delta CG sources. So the natural question is, what kind of d-regular expander graphs will mix well when you use a delta CG source starting at an arbitrary start vertex? And it turns out what you need are expander graphs with great vertex expansion. Namely, we need something called lossless expanders. So I'll tell you the definition now. An undirected d-regular graph is a k epsilon lossless expander for parameters k and epsilon if for every subset of vertices of size at most k, the neighborhood of S is at least 1 minus epsilon times d times the size of S. And so the way you should picture this is for your entire graph, you have some small subset of size at most k, and for every node in your subset, you know there are d edges leaving each node. So in the ideal world, the size of the neighborhood of S will be something like d times S exactly. And so a lossless expander is saying that the actual expansion of this small subset S is within a 1 minus epsilon factor of the ideal expansion size of the neighborhood of S. And so specifically, the way you should think of a lossless expander intuitively for the purposes of this talk is that for any subset of subset S of vertices in your graph, you should think that there are d total edges leaving it, and there are epsilon d here, red edges or bad edges, here epsilon d is 2, that don't contribute to the expansion of S, or say the size of the neighborhood of S. And so every node has epsilon d red edges or bad edges that don't contribute to expansion in some sense. And so now I want to talk to you about how you should picture this graph in the context of a random walk on a delta CG source. And so what I want you to picture is I want you to picture S, the subset of sufficiently small size that you're considering, as the support of the vertex distribution after I steps of a random walk. So what this means is that you could have started at an arbitrary start vertex, and then you could have gotten to any node in S. And so like we said, now wherever we're at, whatever node we're at in S, the adversary, or this adversarial random walk, is allowed to pick big D to the delta here as edges as the subset of possible edges for the next step. And the observation is fairly simple. It's just that if the adversary was allowed to pick much less edges than the total number of red edges leaving a vertex, then you won't get any type of mixing. You won't make any progress because, like we said, if you only take red edges, you won't be expanding at all. And so what we want to say is that the total number of choices that the adversary must make for the next step, the size of the subset of possible neighbors that the adversary must pick from, say uniformly, for the next step, which is d to the delta, must be a lot more than the number of red edges or edges that don't contribute to expansion, namely epsilon d. And if you divide, that just means that you need epsilon at most 1 over d to the 1 minus delta. And so what this means is that if you want to hope to handle any rate delta greater than 0, then you're really going to need an epsilon, this sort of error parameter of the lossless expander, to be really close to this optimal value of 1 over d. Okay, so now that we know what types of amazing lossless expanders we need in order to get our random walks to have any hope that our random walks mix at all, let's talk about what we can actually hope to get for these types of lossless expanders. So non-constructively, we know that there are these optimal lossless expanders that are D-regular, and they are K epsilon lossless expanders with K equal to omega of M. This is not as important of a parameter for the purposes of this talk, and epsilon equal to O of 1 over D, or really basically as close to optimal as possible. And so remember, what we said is that if we want to handle any rate, delta greater than 0, then we really need to have a lossless expander with this epsilon error parameter close to 1 over D. So theoretically, we're in business because we know that it's possible to actually achieve such amazing parameters for a lossless expander. But there's one issue, which is that we actually don't know of any explicit constructions that have this amazing of an error parameter for lossless expanders. And so what this means is that, well, we won't have time to get into the details of how we circumvent this, but this is a very interesting part of our work of how we can actually make everything explicit in our function, our condensing and whatnot. But for now, for the purposes of this talk, I'll just tell you what we can hope to do, assuming that we actually have, say, the best possible parameter lossless expanders. And so I want to note that in order to actually analyze these random walks, we have to use an analysis that's different than what came before, namely because usually prior random walk analyses use spectral techniques, and these are insufficient in this case. For example, there are spectral expanders that might not be lossless. For example, there are Ramanujan expanders with epsilon equal to only 1/2 instead of 1 over D. What this means is that essentially you would need an entropy rate basically close to 1 in order to get any hope of your random walks mixing. And second, and more interestingly, a random walk from a CG source is non-Markovian, meaning that the distribution for the next step does not only depend on what vertex you're currently at, but it also depends on how you got to that vertex. So say you are taking a random walk via a CG source, and you take this yellow path to the current vertex, which is in black, then the distribution for the next step could be this yellow subset of edges. And it might be the case that if you took a different path to the same vertex, say this orange path, then the distribution for the next set of edges could be something entirely different. It could be this orange set. So this is a non-Markovian random walk. It's not memoryless. And so there's also a large amount of work that we have to do in order to actually analyze the quality of the distribution at each step. Namely, it's not just obvious after knowing that epsilon is sufficiently small that these random walks will still mix. There's still the issue of what can we say about the quality of the distribution on the support of the random walk, on the vertex support of the random walk. And so what we are going to show is that we're going to show that the LQ norm for some very small q close to 1 of the vertex distribution at each step is of a very high is a very high quality or very small. And this is a useful measure of the randomness of the quality of randomness in the vertex distribution. And the reason we want to use this very small LQ norm is it helps us be less sensitive to very heavy outcomes in the distribution. So it might be the case that, you have certain nodes in your vertex distribution that are quite heavy, but it's still the case that the distribution overall is of pretty high quality. And what the LQ norm is doing for very small values of alpha, so for Q is very close to 1, is essentially we're having a measure of the quality of the distribution that's much less sensitive to these really heavy sort of outliers in the distribution. And so the main lemma that we show in our work is that if you have a K epsilon lossless expander with epsilon equal to 1 over D to the beta for some parameter beta, remember, if we're considering, say, optimal lossless expanders, you can consider beta equal to 1. And if you have the current distribution, P, of your current vertex distribution, and you have P prime, which is the vertex distribution after one step of your random walk, and if the step of the random walk had entropy at least 1 minus beta plus alpha, so remember this you can think of as if in the optimal case beta is 1, so this just says if your entropy rate in each step is just a little bit bigger than 0, and it's the case that your current distribution is not sufficiently good enough yet, it's not sufficiently mixed well enough yet, then what we can say is that the Q to the Q norm of the next distribution, vertex distribution, after one step, goes down by a factor of roughly big D to the delta alpha times the original distribution's Q norm. So what this is saying, sort of in the language of entropy, is that each step is actually gaining roughly delta times little d bits of entropy. That amount of entropy, which is from the random walk instruction, is essentially being added to the entropy of the vertex distribution. And so if you chain this lemma multiple times, then you get sort of the final corollary that I want you to take away with for the purposes of this talk, which is that basically if you have any delta greater than 0, and you have any, if you have an optimal lossless expander on some arbitrary set of M vertices, then if you take a random walk via a delta CG source for any entropy rate delta, you're going to get a vertex distribution that is close to constant entropy gap. So that is the main result, the takeaway that I want you to get from this talk, and thanks.